This video contains the solutions for the free response problems that I've given you to go with section 7.6. Some of them have average value stuff in them, and some of them don't, but they all have the same basic ideas about what you can do with integrals and what integrals mean. And you can certainly expect one of these on your next test. All right, first one here. Traffic flow is defined as the rate at which cars, okay, so it's a rate, okay? So that means you can think of this as being like a derivative. The rate at which cars pass through an intersection measured in cars per minute. Okay? So any number you plug in here, you're getting a rate in cars per minute. The traffic flow at a particular intersection is modeled by the function, this thing, where f of t is measured in cars per minute and t is in minutes. Okay? So first one, to the nearest whole number, how many cars pass through the intersection over the 30-minute period? Okay, so what we need to understand here is, if you want to know the total number of stuff, the total amount of change of the, whatever this is the rate of, in other words, total amount of cars, then think about the graph. So whatever the rate is, who knows what that thing looks like? I suppose we could graph it, right? Let's do that. Actually, so make sure I'm in radian mode. I am. So we have 82 plus 4 sine of x over 2, and I want to look from x values 0 to 30, and I'm certainly not expecting any negative rates here, so I'm going to set that to 0, and looks like if there's an 82 plus 82, let's make it about 100. See how that works. And then I'll set my y-scale to 10, so it marks by tens. Okay, give me a second to look at that. Okay, so this is the rate at which cars are moving through. Now, if I could label this, this is the f function. So on this axis, we get values that are, this is cars per minute, right? And on the horizontal axis, this is time measured in minutes. Now, there's two things we basically know how to do in calculus with these. We could take slopes or we could take integrals. If I took the slope of this, slope is a measurement of rise over run. It's a rate of change. The units of rise over run would be cars per minute, or cars per minute squared. Now, I don't know what that's supposed to mean exactly. It's like the rate that the rate is changing, sort of like an acceleration, if you will. That's not what we want here. We want the total number of cars. Well, when we take areas, then we're like multiplying, like if it was just a rectangle, we're multiplying dimensions. So cars per minute times minutes, that gives us cars, and that's what we want, the total number of cars. So we should be integrating here. So I'm going to go ahead and do that. In a second, calculate, since I'm looking at the graph, and go ahead and do number 7. I want to go from 0 to 30. And all that area is 2,474. And we're going to round to the nearest car, to the nearest whole number, right? Because it doesn't make sense to have some decimal part of a car, unless you're at the circus or something, I guess. So, part A, 2,474 cars. And we should, just in case something went wrong, we should write down what the integral was. There's the integral from 0 to 30 of the function that they gave us. Okay. Part B. Is the traffic flow increasing or decreasing at t equals 7? Give a reason for your answer. Well, increasing or decreasing, I was talking about the derivative of this, right? If the traffic flow is increasing or decreasing. That, in other words, is the rate of cars more or less? So let's go back to that, and let's go second calculate and find the derivative at 7. So that's number 6. We want the derivative at 7. That derivative is negative 1.87, or 873. So f prime of 7 is equal to negative 1.873. So traffic flow is decreasing. Again, we're looking for cues here for what we should be doing. If you want to know things about increasing or decreasing, well, that's information that we get by looking at derivatives. The derivative was negative, that means it's decreasing. That's probably somewhere in here. Oh yeah, you can see the little x there. It's right about here. What's the average value of the traffic flow over the time from 10 to 15? And then indicate units of measure. Okay, we know how to do that. That's the interval from 10 to 15. That interval is 5 wide, so we would have 1 over 5 there of f of t dt. So let's see. If we did second calculate and found our integral again, this time we want to go from 10 to 15. It's 409.5, say. So that's 1/5 times 409.5. I guess I'll keep 3 decimal places for now. I guess it'd be 496. 496. And going back to my home screen, so 409.496 divided by 5 is 81.899. 1.899. Now, let's think about what the units would be on that. If we want the average value of a function, like if you wanted the average value of your quiz scores and it was measured in points, well, the average value is also measured in points. We're taking the average of this function. So that means the units are whatever the units of this function are. The units of an average value are the same as the units of the function itself. So that would be cars per minute. Right, that makes sense. I mean, we found the average value of this function, so this function measures cars per minute, so the average value of it should also be in cars per minute. What's the average rate of change of the traffic flow over the time interval from 10 to 15? So what's the average rate of change of the traffic flow? So what's the average rate of change of the traffic flow over the time interval 10 to 15? Well, an average rate of change, that means basically finding 2 points. So we're finding the slope between these 2 points, right? These are actual traffic flow values, and then the average rate of change is just the slope between those two. An average rate of change is just a slope using 2 points. So since I already have it graphed, I'll just get the y values. I'll go second calculate, with values for my function. First, the value at 10 is 78.164. And at 15, it's 85.752. And then I'll go back to the home screen and find that slope. So that's 85.752 minus 78.164 divided by 15 minus 10, which is 5. It looks like 1 point, what does that say? 1.517, 1.518 actually, sorry. 1.518. Okay, now that's a slope on this graph. So that would be cars per minute per minute. So that's cars per minute, or you could write that as cars per minute squared. Okay? That's the kind of thing we're looking at in this sort of problem. Next one. A test plane flies in a straight line with positive velocity in miles per minute at time t minutes, where v is a differentiable function. So it's a smooth curve between those, no sharp corners. Selected values are given in this table. Use a midpoint Riemann sum with 4 subintervals of equal length. 1, 2, 3, 4. And they want us to use a midpoint. Where is it? Midpoint sum. So that means I'm going to be using these y values, the ones in the middle of those rectangles. And each rectangle is 10 wide. To approximate this, show the computations that lead to our answer. All right, let's go ahead and do that. So the first rectangle, I'm calculating an approximation for this. So the first rectangle is 10 wide and 9.2 high. Second rectangle is 10 wide and 7.0 wide. Next one is 10 wide and 2.4 high. And the next one is 10 wide and 4.3 high. So that's 92 plus 70 is 162, 186, 229, I think. You can check my math there, sorry if that's off. 229. Using correct units, explain the meaning of this integral. Well, let's see. Let's think about that again. We just took the area of velocity versus time. So think about the units. Velocity here, they told us, is miles per minute, and time is in minutes. So if we take the area under a velocity, those get multiplied together because we're finding an area, miles per minute times minutes. So miles, right? And that should make sense because remember that the integral of a velocity function is equal to displacement, right? So this is the displacement from t equals 0 to 40, right? Based on the values in the table, what's the smallest number of instances at which the acceleration of the plane could equal 0 on the open interval from 0 to 40? Well, the acceleration is the slope of this. So let's see what's going on. Looks like these values increase and decrease back. Notice that these are the same, that the 7s, right? That means that at one point here, the average slope from here to here is 0, which means the acceleration had to be 0 from somewhere to here, right? Then it starts going down, 4.5, then 2.4 and 2.4. Those are the same. That's another place where the acceleration had to be 0, and then it goes up again. So it looks like 2 places. right? Acceleration, because the average slope from here to here is 0, average slope from here to here is 0. Those are two places where, since the slope of velocity is acceleration and this is differentiable, the mean value theorem says it must actually, the derivative of this, which is acceleration, must actually equal 0. So two places. One between between 0, t equals 0, and 15. Because average slope of v of t is equal to 0, and 1 between t is equal to 25 and 30, because average slope of the velocity function is equal to 0 again. And then why do we know this? We need to mention we know this because of the mean value theorem. Right? On the real AP test, you're going to write out mean value theorem, right? All right, part C. The function f defined by f of t is equal to yada 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 is used to model the velocity of the plane in miles per minute. So now we've got an actual function that models what's happening here. According to this model, what's the acceleration of the plane at t equals 23? Well, that's easy. That's just the slope of this at 23. So now we have our calculator, so no reason, don't go finding that by hand, please. Not that it's the hardest derivative in the whole world, but we have our calculator. So we're going to do math 8, that's our end deriv. Our function is 6 plus cosine of x over 10 plus 3 sine 7x over 40, comma x, comma, and we want the derivative at 23. You could also graph that and use the second calculate, use the little dy dx thing, but I think I only need one value, so I'm just going to do it this way. And that gives us negative 0.408. Negative 0.408. And indicate units of measure. It's an acceleration, right? It's a slope of this, so it would be miles per minute, or miles per minute squared. It would be miles per minute squared. We might just say that's probably enough. If they just say, like, what is the acceleration, and they don't say anything about, like, show the computations, that's probably sufficient. But just to be safe, I'm going to write down that the f of t function is velocity, so acceleration at 23 is equal to f prime of 23. That's what we found. Okay, last part. According to the model f given in part C, what's the average velocity of the plane in miles per minute over the time interval from 0 to 40? Well, that's an average value. We want the average of the velocity function from 0 to 40. So from 0 to 40, my interval is 40 wide. So when we find average value, we got to divide by how wide it is of the velocity function, which is that f function they gave us. So again, just since I'm just need one value, let me see if I can bring it up by doing this second entry. Let me go back here to nderiv and see if I can get math 9. Now it's turning it into an fn int. So I want the area under this thing, comma x, comma 0, comma 40. Right? That's the area under this from 0 to 40. And then I want to divide that whole thing by 40. Looks like 5.916. And again, the average value of a function, the units have the same units as the function itself. So that would be miles per minute. If you're really thinking about units here, I just point out to you that the area under a velocity curve generally gives us miles, right? Like it did in part A. But we're dividing by 40. Dividing by 40 what? By 40 minutes, right? So the miles that we would have got from here are being divided by minutes again. So we get the same units, which makes sense. The average value of a function should come out to be the same units as the function itself. So 5.916 miles per minute. And we could just look back quickly here. There's all those values. That looks like a pretty reasonable average, which is not the number that you would get, by the way, if you just averaged all of these. It's not the same thing. Of course, it's using a different function. So, all right.